Okay, so this was Laplace transformation. But what we care about, this is not a math course, this is controls, is to work with systems. So the reason why we care about Laplace transformation is because we want to use that to describe systems. We define a concept called transfer function for linear systems. And the way we define it is that it's the ratio of Laplace transformation of the output divided by Laplace transformation of the input when initial conditions are all zero. So if I have a system, if I have a function that is going to the system, I'm feeding that system with the function, and then it's resulting an output. I take the Laplace transformation of these two functions, and then I divide them. The transfer function represents the relationship that describes dynamics of a system. So that's why I care about transfer functions, because they are describing the dynamics of my system. And notice that they're only defined for linear time invariant systems. Look at this example. I have a differential equation written for this mass spring system with spring constant of ky or k, and then the force being applied to it is r of t, and displacement is shown with y of t. If I take the Laplace transformation of this differential equation and plug in initial values, which are all zero here, I'm going to get this fraction. So the fraction of y of s divided by r of s, when y of s is the displacement or output here, and r of s is the force or input, is the transfer function that describes the dynamics of the system. Look at this numerical example. I have a differential equation with y of t on the left and then u of t on the right. Notice that in the previous differential equation on the right-hand side, I just had delta or 2. I had a number. Now I have a function here, which I don't know the value of. I have u of t. So what happens if I take Laplace transformation and plug in the initial values? Well, if the system is at rest, which means all the initial conditions are zero, then I get this fraction. So I can find the Laplace transfer, find the transfer function, which is the ratio of the output to the input for this system. So this is transfer function. So a lot of the times in this course, we just simply show the transfer function of a system with a block with the input going into it and the output coming out of it. And the letter G or T, capital G or capital T, is what we normally use to show transfer functions. Let's see this cart example. So we have the free body diagram of a cart. If we take Laplace transformation of it, of the differential equation, when F is the force or the input and X is the displacement, what am I going to get? I'm going to get f of s on the right-hand side, and on the left-hand side, I'm going to get m times s squared plus k times capital X, which x is displacement or the output. So then the transfer function is going to be x divided by f equals to 1 divided by ms squared plus k. Okay, so we talked about systems, we talked about transfer function, which is a way to describe them. Now we want to define some properties of a transfer function. One of these properties is the order of a transfer function or a system. So order of a system is equal to the degree of the polynomial in the denominator. So look at this polynomial here. Numerator is just 1, denominator is ms squared plus k. What's the degree of the polynomial here? It's a second degree polynomial, right? So the order of the system is 2. Let me go back a little bit. The denominator has a third degree polynomial, so the order of this transfer function or this system is 3. Okay, so that's one definition. Before we go to other definitions, let's a little bit talk about MATLAB. So MATLAB is very useful for controls, and a lot of people use it in industry and academia. So we might have some uh, definitions here or to define how work with MATLAB. So the first one is how we define a transfer function for MATLAB. We have two ways to do that. We can either first define the letter s or the variable s to be the letter, the famous s letter in transfer functions, and then simply just define our transfer function as two polynomials divided by each other. Or alternatively, we can say TF, the command would be TF of the coefficients of the numerator and then the coefficients of the denominator. So let's see an example. I have this differential equation, system is at rest, all initial conditions are 0. I take the Laplace transform, and the transfer function would be 6s plus 2 divided by 3s squared plus 1. Now I want to define this in MATLAB. So my ODE is this, the transfer function, equivalent transfer function is this, and I want to write the code to define the system in MATLAB. So the first way to do it is to say S is TF of S, and then now that letter S is defined as the letter for transfer functions, I can simply say my system is 6 times S plus 2 divided by 3 times S squared plus 1. Or alternatively, I can say my system is TF of 6, 2 and 3, 0, 1, which 6 and 2 are the coefficients of the numerator, and then 3, 0, 1 are the coefficients of the denominator. What is 0? Well, I have 3s squared plus 0 times s plus 1. That's why I have a 0 here. Okay, now I want to define what poles, zeros, and characteristic equation of a system are. So if I have the transfer function of a system, the equation or the polynomial in the denominator is called characteristic equation. If I solve that, the values that I find are going to be poles of the system. If instead I solve the polynomial in the numerator, the roots of that polynomial are the zeros of the system. So poles are the roots of the characteristic equation, and zeros are the roots of the numerator polynomial. So look at this system or this transfer function. What is the characteristic equation? Well, this, the polynomial in the denominator, is the characteristic equation. What are the zeros of the system? Well, if I solve the numerator, if I solve the equation in the numerator, if I say s plus 1 times s negative 3 equals to 0, and then find what values of s make that happen, make that polynomial be or equation be equal to 0, then I have the zeros of the system, which obviously it's going to be negative 1 and plus 3. What are the poles of the system? Well, the roots of the denominator are the poles of the system. So s equals to 0, s equals to negative 1.5, s equals to negative 4 twice. Yes, we count them. We care about multiplicity. And then the roots of this quadratic equation, which are negative 1 plus minus j. So these are the poles of the system. I have 1, 2, 3, 4, 5, and 6. These are 2. Negative 1 plus minus j. These are 2 poles. So I have 6 poles here. If you freaked out when you saw this and you don't know how to solve it and get negative 1 plus minus j, click on this link and refresh your knowledge of complex numbers. We are going to heavily use complex numbers in this course. And by the way, for complex numbers, some people use I and some people use J. That doesn't really matter. In this course, we are going to use J. Okay, let's see how we find poles and zeros of a system in MATLAB. Well, we can just simply use the commands for it, pole and zero. See this example. I have this differential equation and the equivalent transfer function. I first define my transfer function and then I just call the command 0 and pole, and it's going to tell me that the 0 is negative 4 and poles are negative 2 and negative 3. Okay, so the summary of this chapter is this. Laplace transform converts a function from time domain or t to frequency domain or s. We use Laplace transform because it really helps us with solving a differential equation. It turns a differential equation into a much simpler algebraic equation. We use Laplace transform either to solve a differential equation or to find transfer function of a system, or if we are given the input to a system, it can help us solve a differential equation. Okay. Finally, we are going to have an example. We are given this transfer function and we are being asked what the characteristic equation, order of the system, poles of the system, and zeros of the system are. Next slide is going to include the result or the answer. Please think about it first. What's the characteristic equation, the order, poles, and zeros of the system before going to the next slide.